Hello viewers, welcome to my channel. In the present class, we are going to discuss the topic, the general solution of longitudinal waves in the bars. So before that, first let us write the speed of longitudinal wave in the bars or rods v equal to root of y by rho, or otherwise c equal to root of y by rho. Okay, right sir. Where y stands for Young's modulus, right? Y stands for Young's modulus. Rho is density of that material, density of the material of the rod with which it is made. The general solution of this, the general solution of the wave equation. So wave equation. What is a mechanical wave equation? Dou square z by dou x square equal to 1 by c square into or dou square z by dou d square. So that is I'm writing dou square z by dou x square is equal to, right sir, 1 by c square into dou square z by dou d square. So this is the mechanical wave equation standard form. So here we got this is rho by y. So 1 by c square equal to, we have written rho by y, c square equal y by rho, c equal to of y by rho. Yes. So this is equal to, I am writing 1 by c square is what? Rho by y, dou square z by dou t square, dou square z by dou t square. Okay, right sir. So for this, the general solution of this longitudinal wave equation has the form z is equal f of ct minus x plus f of ct plus x. Function of ct minus x plus function of ct plus x. In that formula, c stands for the speed of longitudinal wave, t is of course the time, x is the displacement of longitudinal wave along the x direction in the time interval t seconds. The displacement of longitudinal wave in the time t at any instant of time t, right? X is the displacement of longitudinal wave. Okay, now here, so let us move that this equation, the solution of this equation, this is the general solution. So the solution for longitudinal wave can also be expressed in complex conjugated form. That is, z is equal to a e power j into omega t minus kx plus b e power j into omega t plus kx. Instead of f of ct minus x, here we have taken this term. Instead of f of ct plus x, we have taken this term, b into e power j into omega t plus kx. Okay, sir. Here a, b are constants. Omega angular frequency, omega equal to pi f, right? K is propagation constant. K is equal to omega by v, omega 2 pi f by v f lambda. Ff cancel 2f by lambda. K equal to 2 pi by lambda, propagation constant. All these terms, so we are very familiar. Now, here there are two boundary conditions. The first one is when the rod is fixed at one point. So at the fixed point of the rod, since there the particles cannot vibrate, the particle displacement is taken as 0. For example, if you consider a bar fixed at both ends, like this. So the first position, say this is x is equal to 0. The second one, x is equal to L. Okay, here we have taken a rod of length L. Okay, the first position x is equal to 0. Then the second position will become x is equal to L. Here both ends are fixed. At the fixed end, because there the particles cannot vibrate freely, the particle displacement is 0. Hence, y is equal to 0. Y equal to 0, or there in the previous expression there we have taken z equal to 0 here. At x is equal to L also, Z is equal to 0. Okay. The second, at the free end, not forced end. Some this is the typographical mistake. You can correct it. At the free end of the bar, the force acting at the point is equal to 0. For example, one end is fixed, the second end is free cell. The second end is free. Second one is free. At the free end boundary condition, because there the restoring force, because the restoring force F is equal to 0, F is nothing but what? Y alpha dou Z by dou X. So this expression we got in the previous derivation. Okay, while we are deriving the velocity of flow, longitudinal wave in the box, there we got the expression. Elasticity modulus is equal to stress by strain, longitudinal stress by strain. Stress is equal to force by area. So from that we have written the force. F is equal to Y alpha dou Z by dou X, where Y stands for what? Young's modulus. Alpha, cross-sectional area of the rod. Dou Z by dou X is the slope. Dou Z by dou X. But in that expression, in this expression, Young's modulus of the metal cannot be equal to 0. This is fixed with a constant value. Alpha, cross-sectional area of the rod is not equal to 0. So y not equal to 0, alpha not equal to 0. But the product of y alpha dou Z by dou X is equal to 0. Here we have written. Therefore, compulsory dou Z by dou X is equal to 0. So the conclusion is, at the fixed end, at the fixed end of the bar, the displacement equal to 0. At the free end, force F is equal to 0. From that, we derive dou Z by dou X is equal to 0. So these conditions are known as boundary conditions. So boundary conditions of vibrations of the rod or vibrations of the bar. This way asked under short questions. One is, at fixed end, displacement is equal to 0. At the free end, dou Z by dou X is equal to 0. Okay, so keeping these 2 points in your mind, so let us move for the vibrational modes of the bar when the 2 ends are fixed, right? Or longitudinal vibrations in a bar fixed at the both the ends. Okay, so let us take this is a rod. Okay, so this is one end, it is another end. Both ends of the bar are fixed, are clamped. Okay, so these are the 2 rigid supports. Here we have taken a rod of length L. Hence, the first position x is equal to 0. The second position x is equal to L. X is equal to L. Okay. Now, applying the boundary condition, because both ends are fixed, both ends are clamped. At x is equal to 0, displacement y equal to 0. At x is equal to L, here also y equal to 0. Okay. So what is the what is the exponential form of solution we have? Y is equal to a e power j into omega t minus kx plus b e power j into omega t plus kx. Right, sir? First, let us apply this boundary condition. Putting x is equal to 0, y equal to 0. So in this expression, you put x is equal to 0. Then y equal to 0. 0 is equal to, right? A e power j into omega t minus 0. A e power j omega t plus b e power j into omega t. Okay. In this, e power j omega t is common. A plus b into e power j omega t equal to 0. But here, e power j omega t not equals to 0. Then obviously a plus b is equal to 0. Hence a is equal to minus b. A equal to minus b. Right, sir? Now substitute this value here. A is equal to minus b or b equal to minus a. So then we will get the expression. Okay. What we get by putting b is equal to minus a, then sometimes there are some printing mistakes, z written, sometimes y written. So this is z or y. So we maintain the same terms. Y is equal to or z is equal a e power j omega t into e power minus j omega x. Okay, since b is equal to minus a, so there we have substituted minus a and a is taking common minus e power j omega x. Right, sir? In these two, what is common? A e power j omega t. Okay. Now e power. So here what we substituted at x is equal to l. At x is equal to l, y equal to 0. Second boundary condition. Here we substituted x is equal to l. Then we got z equal to a e power j omega t into e power minus j omega l minus e power j omega l equal to 0. Here a not equal to 0, e power j omega t not equal to 0. So only the term in the bracket is equal to 0. So then e power minus jkl minus e power jkl equal to 0. E power j theta equal to cos theta plus j sin theta. E power minus j theta equal cos theta minus j sin theta. So accordingly, we can write e power minus jkl cos kl plus j sin kl. E power jkl is equal that one. E power minus jkl equal cos kl minus j sin kl. So substituting these values here, e power minus jkl minus e power jkl equal to, then cos terms will be cancelled. Only the sin terms will be left. That value minus 2j sin kl. Right. So putting this value there, putting this value in the above expression here, putting that value here. Okay. In this, right, we simplified this bracket term. So this is equal to 0. So then minus 2j sin kl must be equal to 0. Here 2j, j square is some imaginary j square equal to minus 1. So compulsory sin kl must be equal to 0. Sin kl equal to 0 when it is possible, when kl equal to n pi, n equal to 1, 2, 3 and so on, because sin pi 0, sin 2 pi, sin 3 pi, 4 pi and so on. Hence k is equal to n pi by l sir. K is equal to n pi l. But we know that the propagation constant k related with the angular frequency omega is k equal to omega by c. Right, sir? But k is equal to 2 pi times to the general frequency, normal frequency, 2 pi f by c. Okay. Substituting this value here in this, then k is equal to n pi by l, that is 2 pi f by c is equal to 2 pi f by c is equal to n pi by l, equal to n pi by l. Okay, pi cancel. Then f is equal to nc by 2l. Okay, so from this we are writing f is equal to nc by l, right? F equal to nc by l. That is the frequency of nth mode of vibration. So this one, f is equal to nc by 2l. Here n, n represents number of this waves. If n is equal to 1, then f1 equal to c by 12. If n equal to 2, we can observe here one crest and one trough. So like this. Okay, if n equal to 3, then you can observe this is 1, 2, and 3. 3 ripples, right? F is equal to nc by 12. In this, f1 equal to c by 12 is called fundamental frequency. F2 equal to 2c by 12, that equal 2 times to the fundamental frequency. This is called second harmonic or first overtone. Second harmonic or first overtone. When n equal to 3, then we got F3 equal 3 into c by 12. 3c by 12. 3c by 12, not 2c by l. 3c by 12, that equal 3f1. Okay, it's correct. F1 equals c by 12. Here n equal to 3 substitute, then 3c by 2l, not 2. So you correct this one, 3f1. This is called third harmonic or second overtone. Right, sir? F1 equal to c by 2l is called fundamental frequency. F2 is equal to 2c by 2l, that equal to F1 is called second overtone, second harmonic or first overtone. F3 is equal to 3c by 2l, that equal 3f1. This is called second overtone or third harmonic. Third harmonic. Clear, sir? So the modes of vibrations. The longitudinal modes of vibrations in the bar, which is clamped at both ends, which is fixed at both ends, is given by F is equal to NC by 2N. Okay, N is number of ways where N represents the number of mode. Okay, nth mode of vibrational frequency NC by 2N. For the fundamental frequency, you have to substitute N equal to 1. For the first overtone or second overtone, you have to substitute N equal to 2. So that is called second harmonic mode vibration or first overtone mode of vibration. For N equal to 3, F3 equal to 3F1. This is second overtone mode of vibration, or we call it as third harmonic. Similarly, the fourth harmonic, fifth, sixth, and so on, you will get 4F1, 5F1, 6F1, and so on. The first fundamental frequency, F1. Second harmonic, 2F1. Right, sir? Third harmonic, 3F1. Fourth harmonic, 4F1. Next, 5F1, 6F1. Therefore, the ratio of fundamental frequency to the other harmonics is 1 is to 2 is to 3 is to 4. The overtones frequencies is equal to integral multiple of fundamental frequency, because 2F1, 3F1, 4F1, that 2, 3, 4 integers. The frequencies of the overtones are the frequencies of the harmonics existing in the vibrational bar clamped at both ends is integral multiple of fundamental frequency. Or we can say that the ratio of fundamental frequency and other overtones will be 1 is to 2 is to 3 is to 4 and so on. Okay, so this is the concept we discussed in this class. Right, sir?